Remember in our time dilation video, we had a little boy go off in a rocket ship at speed v relative to a little girl, and we considered the situation from the little girl's reference frame. The boy's t-axis was slanted with slope 1 over v, and the boy's x-axis was also slanted with slope v. Let's watch them take their little trip. As they both travel through time, the boy is moving further and further away from the little girl. You'll notice that the little boy and little girl are simultaneously across from one another, and lines of simultaneity are horizontal in the little girl's reference frame, so this would be the picture from the little girl's perspective. If the girl measures a time t for the trip, then she would measure her distance from the boy to be vt. Let's look at this trip again from the little boy's point of view. Since lines of simultaneity are sloped according to the boy, he measures the girl to be at a position indicated by the dotted blue line, and when he finishes his trip, the girl has not yet reached position t on her time axis. If the boy measures a time t prime for the trip, then he will measure his distance from the girl to be vt prime. As an aside, it is interesting to note the time experienced by the girl at this moment. Let's call it tau. Looking at the yellow triangle, it is clear that the slope of the blue line, v, is equal to rise over run. In other words, the difference between t and tau, divided by vt. Rearranging to solve for tau yields tau equals t times 1 minus v squared. Recalling the relationship between t and t prime from before, we can substitute this into the previous equation and get a relationship between t prime and tau. Notice that these last two equations have exactly the same form. The girl thinks that her time t is greater than the boy's time t prime, and the boy thinks that his time t prime is greater than the girl's time tau. So the situation is completely symmetrical, and whose clock is running slower is a question that is reference frame dependent. Anyway, back to a derivation of the Lorentz transformations. We are now in a position to scale the red and blue time axes. Let's start with the red one because it's a little easier. Since t equals t prime over the square root of 1 minus v squared, we can simply label the last t coordinate t prime over the square root of 1 minus v squared. To get a feel for how the red and blue axes scale together, let's label a few other coordinates. Let's label 1 and 1 over the square root of 1 minus v squared, 2 and 2 over the square root of 1 minus v squared, and 3 over the square root of 1 minus v squared. Okay, now it's time to label the x-axes. If we multiply the time dilation formula by v, we see that the length of the red horizontal line vt is equal to the length of the blue horizontal line vt prime divided by the root of 1 minus v squared. So this is the relationship between red horizontal lengths and blue sloped lengths. Let's see how that looks on the x-axis. Now that we've scaled the red and blue axes, it's time to look at an event that happens in spacetime. Let the coordinates of the event be x prime, t prime, according to the boy. What will the girl's coordinates x and t be? Let's find out. To visualize the boy's measured distance x prime, draw a dotted line parallel to his t prime axis, down to his x prime axis. His x prime distance can be visualized as the shaded part of his x prime axis. The boy's measured t prime can be visualized by drawing a dotted line from the event to the boy's t prime axis, parallel to his x prime axis. Let's shade in the boy's t prime axis up to that time. Now let's look at the girl's x-coordinate by drawing a dotted line from the event down to the girl's x-axis. This distance is made up of the distance x prime over the square root of 1 minus v squared, plus another distance that we will shade green. This green distance is equal to the original distance the boy traveled because these two triangles are congruent. From the leftmost purple triangle, we see the slope of the blue line is 1 over v, which equals t prime over the root of 1 minus v squared, divided by the length of the green line. Rearranging this formula yields the length of the green line equals vt prime over the square root of 1 minus v squared. Since the girl's x-coordinate is the yellow line plus the green line, we obtain the full Lorentz transformation for the girl's x-coordinate, which is x equals x prime plus vt prime over the square root of 1 minus v squared. To find the event's t-coordinate according to the girl, we again use the congruency of the two purple triangles, and we see the length of the pink line is just t prime over the square root of 1 minus v squared. But what about the rest of the t-coordinate, namely the orange line? The orange line is the same length as the red dotted line, and we can find this length by considering the relationship between the sides of the cyan triangle. Since the slope of the blue line is v, we have that the slope v is equal to the orange line divided by x prime over the square root of 1 minus v squared. Solving this equation for the orange line, we obtain the orange line is equal to vx prime over the square root of 1 minus v squared. The t-coordinate is equal to the pink line plus the orange line, and is therefore equal to t prime plus vx prime over the square root of 1 minus v squared. These equations for x and t in terms of x prime and t prime are the famous Lorentz transformations. Thank you for watching.